I'm Zhao from Tokyo Institute of Technology, and I'm going to introduce our work, Polarimetric PatchMatch Multi-View Stereo. First is a brief introduction about our PolarPMS, which is a PatchMatch Multi-View Stereo method using polarization information to help estimate 3D information. The inputs are polarization images captured by a polarization camera from multiple view directions, and our PolarPMS estimates depth and normal maps for each view and merges them to the 3D point cloud. Our contributions are summarized as follows. First, we propose the first PatchMatch MVS method using polarimetric information. Second, we introduced effective polarimetric consistency evaluation to PatchMatch MVS. Third, we demonstrated the state-of-the-art performance, especially for textureless regions. Next is the overview of PatchMatch MVS. Each input RGB image is selected as a reference view in turn, and corresponding source views are selected according to geometric pairs proposed by CoMap. After view selection, depth and normal of the reference view are initialized randomly. From the initial values, depth and normal hypotheses are then generated for further evaluation. These hypotheses are evaluated by calculating photometric consistency among different views, and the hypothesis with the highest consistency is selected as the current estimation. The above process is performed pixel-wisely in 4 different scanning orders. The estimation is performed iteratively until reach the iteration limit. At last, depth and normal maps are derived as the output. For the overview of our proposed PolarPMS, a PatchMatch MVS method with polarization images, depth and normal hypothesis is evaluated not only by considering photometric consistency, but also polarimetric consistency using information from AOP and DOP images. Next, I would like to introduce the depth and normal hypothesis generation and evaluation. For the generation of depth and normal hypothesis of a certain pixel, we consider the current depth and normal estimation, the propagation from adjacent pixel, randomly generated depth and normal hypothesis, and perturbed depth and normal hypothesis from current estimation. After the generation of depth and normal hypothesis, they are projected to the 3D space. Those 3D patches are then projected to the source image plane, and the evaluation can be performed for each depth and normal hypothesis. This is the cost function for evaluating depth and normal hypothesis. We consider photometric consistency, geometric consistency, polarimetric consistency, and depth and normal consistency. Cost for each depth and normal hypothesis is calculated, and the one with smallest cost is selected. Among these consistencies, I would like to explain more details about the polarimetric consistency, which is the key part of our proposed method. Before the introduction of polarimetric consistency calculation, I'd like to explain the physical relationship between polarization and surface normal. When the light is reflected from the surface of an object, the status of polarization changes. The angle of polarization, AOP, which indicates the direction of the strongest electric field of the light, can reveal information about the surface normal. Although the relationship between AOP and surface normal changes according to the illumination conditions, the material of the object, and the viewing direction, they are highly related. Briefly, the azimuth angle, the angle between x-axis and the projected normal in the image plane, can be inferred from AOP, which equals AOP has pi or half of pi's difference with AOP. As introduced before, the depth and normal hypothesis is projected to a source view, as shown in the left part. The azimuth angle can be calculated from the normal, and the projection to AOP image corresponds to an AOP value. From this AOP value, 4 possible azimuth angles can be inferred, and we calculate the minimum difference as the polarimetric cost. Polarimetric information helps improve the estimation of normal directly, And we also introduce depth normal consistency to refine depths using the more accurate normal information. Next is the introduction about the simulation. We use Mitzvah 2 renderer to synthesize polarization images. We set cameras around the object and set an environment map as the illumination. In front of each camera, we set a linear polarizer, which is rotated to 0, 45, 90, and 135 degrees to capture polarization images. Generated RGB, AOP, and DOP images are shown on the right. Simulation results of depth and normal maps are shown in this page. We compare our PolarPMS with CoreMap, which is the base of our method, and ACMMP, which is the state-of-the-art PatchMatch MVS method. The numerical evaluation of depths and normals is shown on the left, where the vertical axis represents the proportion of the pixels whose errors are less than the threshold of the horizontal axis. It can be seen that our method recovers best accuracy, especially in normal estimation. Visual comparison is on the right side, which can again demonstrate the effectiveness of our proposed method. Next is the result of point cloud, which is recovered by fusing depth and normal maps. The table summarizes the accuracy and completeness of point cloud results. Our proposed method achieves the best average accuracy and completeness using all three models. The visual comparison on the right illustrates that our method generates the most accurate and complete point cloud. As for real scene experiments, we use one-shot polarization camera to capture the data. The sensor pattern is shown at the bottom right of the page. RGB information and polarimetric information can be obtained in one shot using this kind of camera. Next is about the polarization data acquisition. We perform demosaicing to obtain full-size polarization images, denoted as I0, I45, I90, and I135. These images are then used to calculate the intensity information and polarimetric information, including the angle polarization AOP and degree of polarization DOP. This page shows the results of a toy car. Input RGB, AOP, and DOP images are at the top left. Camera poses are on the right, and visual comparison of recovered point clouds are at the bottom. It is clear that our proposed method can reconstruct the most accurate and complete result. We also compare our method with Polarimetric MVS, which is an MVS method using polarimetric information without checking multi-view consistency, compared to CoreMap, which does not use polarimetric information. Polarimetric MVS and our PolarPMS achieve more complete results. Polarimetric MVS recover very dense points, and our proposed PolarPMS recovers more accurate points by evaluating multi-view consistency. In conclusion, we have proposed PolarPMS, a new PatchMatch MVS method that can achieve better accuracy and completeness of reconstructed 3D models. It exploits polarimetric information to improve the accuracy of the surface normal and depth estimation, making use of the physical relationship between AOP and azimuth angle of the normal, and also can realize better completeness, especially for textureless regions. Our code is also available on our homepage. Thank you.